Thân chào mọi người, cảm ơn mọi người đã đến với buổi webinar tháng 4 của VCA. Và như mọi người đã biết thì cộng đồng hóa học Việt Nam VCA được lập ra với mong muốn là nơi để mọi người trong ngành hóa chia sẻ những kinh nghiệm, nghiên cứu và kết nối với nhau. Đến với buổi chuyên đề ngày hôm nay thì VCA vinh dự nhận được sự đồng ý chia sẻ của tiến sĩ Phạm Tuấn Anh. Thì hiện anh đang công tác tại Viện Nghiên cứu Quốc gia Hoa Kỳ Lawrence Livermore, California. Và anh tốt nghiệp Ph.D. ngành hóa lý từ Đại học California Davis và bắt đầu vào Viện Nghiên cứu Quốc gia Lawrence Livermore vào năm 2014. Thì anh tập trung nghiên cứu và phát triển các ứng dụng của kỹ thuật mô phỏng vào việc xác định và hiểu và dự đoán các tính chất vật liệu cho ứng dụng trong năng lượng và môi trường. Ví dụ như là bao gồm pin ion siêu tụ điện, sản xuất hydro thông qua solar water splitting và khử muối trong nước. Tiến sĩ Tuấn Anh là tác giả của hơn 50 bài báo đã được bình duyệt với hơn 1.600 lượt trích dẫn và chỉ số ActionNet là 20. Thì anh cũng là chủ nhân của rất là nhiều giải thưởng, bao gồm các giải thưởng dành cho bài báo khoa học xuất sắc, nghiên cứu xuất sắc và mentor hướng dẫn xuất sắc của Viện Nghiên cứu Quốc gia Lawrence Livermore và Penn Conference in Theoretical Chemistry Postdoc Fellowship. Và hôm nay anh sẽ chia sẻ với VCA về việc dùng kỹ thuật mô phỏng để dự đoán cấu trúc vật liệu cho năng lượng tái tạo, xử lý nước và cũng như xử lý những vấn đề thực tiễn khác như là vấn đề ăn mòn. Ngoài ra, vai trò của trí tuệ nhân tạo và data science cũng được thảo luận trong chuyên đề ngày hôm nay. Thì để buổi chia sẻ được diễn ra suôn sẻ thì em xin nhắc mọi người mute microphone và các câu hỏi xin mọi người đặt qua khung chat của Zoom hoặc là live trên Facebook. Hoặc mà muốn trao đổi trực tiếp với anh thì xin raise hand và trao đổi trực tiếp. Thì em xin được chuyển mic cho anh Tuấn Anh. Em xin mời anh ạ.
Em cảm ơn mọi người, rất là exciting mình contribute cái talk này. Thì mình cũng xin phép chia sẻ bằng cái talk này bằng tiếng Anh cho nó tiện lợi cho the scientific discussion. So again, want to thanks everybody for being here, especially the organizer. Really exciting be part of it. So what I'd like to talk about today is to share with you some of the work that I has been doing in the past 5 or 6 years or so in the areas of simulating materials for energies and water applications. So, just to begin, is talking about, to start with the motivations, like why we care about materials, and it's actually quite interesting to look at, the developments of human histories and what we see in the histories of human is that, our civilization is actually driven by advancements in material, right? So we start with the Stone Age, and then we go to Bronze, Iron Age, and right now we would say that we are in the Silicon Age. So what we see here is everything is actually driven by materials, and it's also interesting to see that if you look at this picture, we go from very simple materials like stone, and then we become smarter, and we try to make a more sophisticated materials, right? And at this point, if you look at this chip, for example, it's highly complicated. It's a lot of components into that. So that is going to the next one. It's also related to another point I'll try to make here is that if you look at simple device that we have been using, the one that we are using every day is like smartphone, for example. It turns out that is a very complicated device, right? And to make that, you actually use almost all the elements in the periodic table, right? So at this point, I mean, the challenge for material development is not only to have a new material, but also how to integrate different components of materials or device so that we can have we can reach a certain functionalities that we want to have. So that is one challenge. Another one is to make sure that we can have a cheaper device, or we want to replace the certain elements with something cheaper or something more environment friendly. For example, in the battery here, what we know here is that we relies a lot on not only like carbon, oxygen, but also some elements like copper, and it is expensive, it is toxic, so that's something we want to replace, right? Another example here is about some of the elements that we're using in batteries, so-called the rare earth elements, even though it's a very small amount of that we are using, but it's rare. It's not easy to take that to receive or to have that elements in the large amount. So that's something that we need to think about. We need to replace those elements by something else. So that requires a whole new paradigms of design, right? So really, so if you look at that, overall, the next challenge in material development is not only like new materials, but also how to integrate different components of the materials in a unique way to reach a certain functionalities that we want. Not only to address the challenge in energies and water, but also basically everything else. So sort of going to the next point, we know that material development is complicated, so that it is slow, right? And it's sort of like this picture, because it's very nice review and sort of tell us like how much time we need to spend for material development. And it's remarkable to see this picture, like, basically tell us like we need to spend like 20 years on average to develop anything. Like, for example, lithium battery take about 20 years. Fuel cell gallium arsenide that we use in the semiconductor device. Teflon for cooking, for example, is another thing. So it takes about 20 years, right? But then at the same time, you look at how much time that we get from from a investor, like government or private company. Typically, the time that we have to do research is like 5 years, 3 years, depending on the company as well. And then also the investments on the manpower, right? For the student, we have like 5 years as a Ph.D. and then you leave and you sort of losing the expertise in the group and so on. The same even shorter for postdoc, because you don't want to spend like 5, 6 years doing postdoc. You want to have like 2 or 3 years and then you move on. So the investments, there is a big gap between what we expect from the real life, like we need 20 years to develop material, and the investment is like much shorter, like 3 to 5 years. So clearly there is a gap, and with the current situations, what we really want to have is to reduce the times that we need to develop material. So that is a challenge. Material development is slow. So the question is, how can we accelerate the material development? And this idea is not new, right? So it has been proposed for sometimes from like almost like 10 years ago from the Obama administrations. And the idea is by using simulations and modelings to accelerate material development. So for this, the ideas relies on 3 components, right? So first one is that right now we have advancements in simulations and modeling. What it means is that we can compute the quantities that like 5 years ago, we don't know how to compute it. We can use the simulations and modelings to look at the realistic system. It's not a toy model anymore. So that is one component. The second component is highly related to the first one, is advancements in high performance computing. We have a big computer now, everything is cheaper, so we can compute everything faster. We can also collect more information. So that these 2 components actually lead to the third one, which is about data science and machine learning. What it means is that now I have a code, I have a high performance computing, and then I can generate a lot of data. So the question is, how can we leverage this data and then, learn something better? So that is a role of data science, machine learning. So that's the reason why, the trend right now is really not only relies on experiments. Instead, we're going to try to integrate simulations, experiments, data science, machine learning, really try to accelerate material development. And the goal, even like 10 years ago, that's so-called, in the material genome initiatives more than 10 years ago, is to use this combination of techniques to really shorten the cycle, the time that we need to develop materials by 50% or so. So that is the whole ideas, and hopefully in this talk I try to convince you that we can use simulations and modeling to help to understand materials properties for different applications. And at this point, I want to sort of tell you a little bit about what I really want to do and in my research. And so the type of research that I really passionate about is to understand materials interface for energies and water systems. And the type interface that I passionate about is a solid liquid interface. And the reason is that as long as we are able to understand the physics and chemistries of what happenings at the solid and liquid interface, you can really apply that to many different systems, right? And here's just to show you three examples. One is in the areas of desalination, water treatment. The second one is about energy storage. It's like ion battery, supercapacitor, and then the third component is about solar water splitting, but it can also be applied to other things like CO2 reduction, so on and so forth. So, just to explain a little bit here, like why solid liquid interface is important. If you look at the water treatment like a membrane, or we need to understand, the very first thing we need to understand is how the selectivities of the ion is governed by the porosities of the membrane, and also how does that interact with the membrane, basically determine the selectivities of the systems, right? Similarly, in the energy storage device, like supercapacitor, you have an electrode and you have the solutions on the right-hand side. You apply the potential and the ion absorb on the surface, and you want to understand how the ion is, the so-called electric double layer is formed on the surface. And the detail of that electric double layer basically govern the performance of your device. So again, it's solid liquid interface, a little bit different properties and applications. And the final example is in the areas of energy conversions. In this way, the picture here is about the photoelectrochemical cell that we use to generate hydrogens. And again, you have a solid, in this case, is a semiconductor that absorbs sunlight. On the right-hand side is solutions. The way it works is the absorber absorbs sunlight, we get electron hole pair in the system, and then that reduces water to generate hydrogen, right? So in this case, what you need to understand is also what is the behavior of electron charge transfer at the interface, and also the chemistries at the interface, and how does that influence the stabilities of the material. So all of these examples is just to show you how important it is to understand the solid liquid interface. And the dream is, if you are able to build the simulations and modeling capabilities to understand solid liquid interface, you can really apply that to understand a lot of different applications. So that is a dream for the simulations people like me. So this come to the point of, what we want to do in this talk is two things. One is to sort of go very quickly about some of the basic concept of the type simulations that we are using in my group. And second is to show how we use simulations and modelings to look at different applications and sort of try to convince you that yes, simulations, modeling certainly is useful. It can provide useful information for material development. So talking about the simulations, right, this picture is sort of useful. The type of simulations that I was trained to do is in this area. So it's nanoscale simulations. So that means at this point, you sort of care about atom, you care not only about the atoms, but also electron. And the thing that is different from the other scale, like the macro scale. When we talk about macro scale, it's like the motion of an apple, you know, or the ball. So it's different, right? So the difference between these two scales is underlying physics, right? So in a nanoscale, you care about electron. So to understand the material, you need to solve the so-called Schrodinger equation. Okay. In a macro scale, it's not really matter. You use another equation. In this case, a Newton equations. For example, when you try to understand how the apple falls from the tree, you can solve it using Newton equations. In the between here is so-called a meso micro scale, which is everything become less clear, but it is certainly not the expertise and also not the topic of this talk. So I'm going to talk about what we are using as a sort of simulation techniques that we use to understand atoms and electrons at the nanoscale here. So this is actually the dream for any simulations people, right? So the dream is we can predict anything from first principle. So what it means is, if any of you come and tell me, hey, I have these materials, I know the compositions of this material, whether it is silicon, it is gallium arsenide, it is water, and then I can tell you what is the properties of that material. I don't need any other information from experiments. So that is a dream. And why is that? Well, the principle is that, if I know the compositions of the materials, I will solve the Schrodinger equations, and then the Schrodinger equation tell me everything about the system, So that is a dream. Now, certainly in practice, it's going to be very different, right? In practice, you cannot solve the Schrodinger equations for a complex system. And in principle, you can solve the Schrodinger equations for the hydrogen molecule, which is not so useful for material design. And so you need to make the approximations, right? And is the heavier approximation you're using, and then it's become less accurate, but at the same time, it allows us to study larger system. For example, you can, things like density functional theory, that is something we use heavily in material science study. We can use that to study system up to 1,000 atoms or so, right? But it's still, in many cases, not enough because, for the realistic system, many times that 1,000 atoms is not enough, 10,000 million atoms is not even enough. So what I mean here is that we really need to take the balance, right? And the trick here is that depending on the properties that we want to look at, really you need to choose the right tool, the right approach to use. So that come to this slide. Just want to show you the sort of tool set that we has been using in my group, in the quantum simulations group. And it really depends on what you really want to look at in your system. So say, if I want to understand electron, or I want to understand the bond breaking, or I want to have a very high resolutions of ion and solution and so on. And then definitely you need to go to quantum simulation. So that means density function theory, quantum Monte Carlo, so on and so forth, right? But then if you don't care a whole lot about electron, and I want to understand, for example, the transport of atoms in the solution at the interface, and you need to have a longer time and larger system to deal with. And then, we sort of use as, classical simulations, and if you solve the Newton equations for the atoms, and then you approximate the effects of electron in a simple way, right? Now you can also choose something in between, so-called a hybrid approach. For example, you want to look at the surface or interface in the presence of an electrolyte, for example, and you really want to have a high accuracy of the certain reactions at the surface here, and they don't really care so much about the electrolyte far away from the interface, for example. Then you can use this hybrid approach. So that means you treat the area that you care about using quantum simulations, and then the rest of the system you just describe with some simple continuum classical model, right? So this just to tell us, like, different type techniques that we can use, and it's really depending on the problem that we want to look at, and also the material that we want to look at. So with that, I sort of want to tell you a little bit about how we use different techniques to understand materials for different applications. And in this talk, I just want to give you a few examples about, one is about hydrogen's productions through solar water splitting. The second is to understand carbon-based supercapacitor for energy storage. And then I talk a little bit about materials for separations and water treatment. So start with the hydrogen productions through solar water splitting. So that is type of simple device that we have in mind, and it has a solid semiconductor on the left-hand side, water on the right-hand side, and the principle is pretty simple. The left here, you absorb sunlight, create electron hole pair in the system, and then these electron and hole migrate to the surface and reduce water, and then we create hydrogen's molecule eventually, right? So the challenge here is really sort of interesting to look at this, like the material that is efficient for the absorption, it tends to be not stable in the solutions. Like, if you look at this table, I mean, like the semiconductor that we're using, especially like 3-5, it tend to absorb the sunlight very well, but then it's not stable at all in the solutions. On the other hand, the metal oxide, for example, is very stable in the solutions, but then it tend to not absorb very well, visible light. So eventually, what we really want to understand in this system, first is, the charge transfer process at the solid liquid interface. And second is the interfacial chemistries and how does that influence my stabilities of the material. And certainly understanding or improving material stabilities and also understanding the mechanisms of corrosions, degradations of materials is basically the key in order to realize these technologies and make it become you can really apply it, or start to market that technologies. So the first thing I want to talk about is, from the simulation side, how we can describe the electronic properties of the solid and liquid, because that's what we want to do here. The first step, we need to look at the electronic process at the solid liquid interface, and then the first thing is to look at the liquid and the solid individually, right? So talking about experiments, the way that you sort of understand the electronic properties of the solid or the band structure of the solid is by using photoemission spectroscopy, right? Well, for example, if you want to understand valence band maximums of the solid, the way you do it is, you send a photon in, and then it's remove one electron, and then you measure the difference between the energies of the photons and then the kinetic energies of the electron that give you the energies of the valence band maximum or the occupied state. You can also do it in a reverse way, so-called inverse photo emissions. So that's going to give you the information about unoccupied state here, right? Now, for the solid, is very well-known procedure. You can do that in ultra-high vacuums. So you can really carry out the emission spectroscopy to understand the electronic structure of the solid very easily. For the liquid, a little bit trickier, right? Because you always have some sort of vapor, and then there is a high chance that the electron that you pick out is sort of interact and with the vapor, and then the measurement become less reliable. But anyways, there is another technique that people can use, and pioneered by Winter group here. They so-called the liquid microjets. What they can do is they can look at the spectrums, and then they can tell what is the signature of the photoelectron. So you can tell, like, okay, the first band here has become to what type of molecular orbitals of the water, right? At the same time, for simulations, there are a bunch of things that we can do, mostly, quantum simulations, because really we look at the electron picture, we look at the behavior of electrons, so it's really has to be quantum simulations. Many times we use Ph.D. and many-body perturbations theory, which is more accurate than the conventional density functional theory. But what I really wanted to show you here is just one example of how the experiment look like, and how the spectrum look like. So this is a spectrum of the sodium nitrate solutions. What it can tell us is like, okay, the first peak here is coming from water. It's a 1B1, and this is how the molecular orbital look like. But then you can also extract information of the ion, right? So this peak around 10 EV is so-called ionization potential of the nitrate in the solution. So that type simulate, this the type experiment. It is type information that you can get from experiments. Now the question is, can we simulate that? Can we predict that from the simulation? So some time ago, this is what we did, and the very first thing we try to do is to build a framework to understand the electronic properties of liquid water first, right? So the procedure is following. So you sort of put a number of water molecules in a box, and then you run the molecular dynamic simulations, and then you have a configuration. You use the electronic structure calculations. In this case, GW approximations, many-body perturbations theory. But anyways, the main things that I want to show you is on the right-hand side here. So if we look at the center here, so-called the quantum bulk. Below is valence band, and the upper is conduction band. And you see here, the calculations that we obtain is about 10.2 for the valence band, agree very well with experiments. And I just want to tell that, this type of agreement cannot be achieved with a conventional approach like density functional theories. Really need to go at the higher levels theory in order to get this agreement. But also another thing that is quite interesting is that, if we also look at the so-called nuclear quantum effects of the hydrogens, and what is found is that if we start to make the hydrogen become more like quantum behavior, and then you start to see like the hydrogens start to see each other, and then everything become overlap, and then that's the reason why the band gap between like the valence band and conduction band, when you take into account the quantum effect, is actually smaller if you don't take into account the quantum effects, right? Another thing that we see is, the question is, how about I look at the surface of the water surface instead of bulk water? And what we see is that, at the water surface, what happened is you have a whole lot of broken hydrogen bond. So when you have a broken hydrogen bond, that means the conduction band of water become more localized, and that's the reason why it becomes smaller, lower in the energies. So the implications for this is really about Well, this really depends on what is the state that experiment is probing, right? In the experiments, like if we probe the state on the surface or in the book, it's going to give you a totally different result. And it really depends on the techniques or the detail of the experiment. So that is something we learned from the simulation here, and also sort of suggests this experiment to do that. Now, to move another step forward is like, hey, in realities, it's not only pure water. I want to have something to re-electrolyte, right? So we need to put the ion in that. And then we see, okay, can I predict the electronic properties or energy level of those ions? And the answer is yes, using the same similar approach. What we try to compute is ionization potential of the ion. And you see here is a comparisons between experiments on the X and the theories on the Y here. And you see the very good agreement between experiments and simulation. Again, this can only be achieved at a certain level of theory, especially, a high level first principle calculations. So now we are able to describe the electronic properties or electron behavior of the liquid and the solid. Now we can put them together, and that is a final goal, right? We want to understand how the charge is hopping from one side to the other side, and that is a really, define efficiencies of the hydrogen's productions. So what we did in this study is really, okay, we put the silicon in contact with the liquid water, but then we also want to play a little bit with the surface here. And instead of using the pristine silicon surface, we actually try to terminate that with different functionalities. So functional group, actually, so we terminate it with the hydrogens and CF3, CF3, so on and so forth. So this is also, the type of functional groups that is, interested by the experiments. So what we show here is that, forget about all the detail here, but let's look at the blue box here. Okay. So what we see here is that the alignment, so the VBM is a below bar here, the lower bar, and the alignment between the blue bar and the level from water is a -1 line here. This really depends on type of functional group that you have, right? So if you have a hydrogen, it's lower, CF3 is lower, but then if you change to like CA3 or COOH, and then, the same story totally changed. So what it means here is really, we show that by doing this type of simulation, I mean, we show that the charge transport of the solid liquid interface can really be manipulated by changing the surface of the materials. And the underlying mechanisms that just sort of defines this alignment is due to the dipole moment, the polarizations at the surface, but also it's because of the rearrangement or the orientations of the water at the solid liquid interface. It's quite complicated, but with this simulation, we can really elucidate, we can really understand all of that effects together. So that is another example of how, using simulations and modeling, we can sort of help to understand what is really going on in the experiments. Now, we want to talk a little bit about material stabilities, right? Chemistry. It's not only about the transport of electron, but also we want to understand where the material is stable in the solutions. So usually the way we do that is by using combinations of first principle molecular dynamic simulations. And recently we also start to look at the mesoscale simulations. So what we're doing is, well, we take a surface like this. In this case, 3,5 gallium phosphide, and you put that in the solution, and then you run the molecular dynamic simulations. You can also try to compute the kinetics of how much energy basically to remove one atom from the surface and bring it to the solutions. So that is basically the kinetics for the dissolution, right? Where the atoms or the surface is stable. And then you can use that as information as the input to turn it into in the let me see, in the mesoscale here. The movie is not running, but it's just to tell us like how the materials is dissolved, right? So the whole idea is to use a sort of combinations of different techniques to predict the material stabilities, dissolutions, and passivations of the surface in the presence of aqueous environments. So that is one example. But then the one thing I want to show is a work that we done with experiments recently on silicon gallium nitride for hydrogen productions, and here's a system. That's how it looked like. You have silicons, and then you have gallium nitrides on top of it, and the way it works is like this gallium nitride really protect the system, and at the same time make it can actually help to facilitate the productions of hydrogen as well. And what we see is really there is a transformations of the chemical reaction, chemical transformations that really facilitate and improve the material stability. So what we find is after some time, when you put the gallium nitride in the solutions, it turned out that on top of the material, they only form the so-called gallium oxide only. So there is no nitrogen. On the wall here, actually, they form a sort of composition between gallium, nitrogens, and oxygens at the same time. So the role of the simulations and modeling here is to try to understand, to understand better why it happened, right? So the calculations that we did here is to show here, if we look at the top surface, the most stable configuration is actually only gallium and oxygen on the surface. So that is consistent with the experiments. Now for the wall, it's different orientations, and again we see that the top surface, the most stable configuration is actually the combinations between nitrogen, oxygen, and galliums. So using these simulations here, you can confirm, not only confirm the experiment finding, but also we show that the reason why there is a difference between the top and on the side wall here is just because of the change in the polarizations effects between the two surfaces. So I want to ask how many minutes that I have then?
You can still have as many as you need, Anton.
Okay. Thank you. Yeah. All right. Almost. Okay. So the next one I want to try to be quicker here is of talking about current-based supercapacitor for energy storage. And this really quick introductions about a supercapacitor or electric double layer supercapacitor. And the principle is very simple. You have electrode, and then you have electrolyte, you apply potential, and then you have ion absorb on the surface, right? So how it works here is that, you can think about this as a parallel capacitor, right? But then the ion is so close to the surface. So the distance between the positive and the negative side is very small. So that's the reason why the energy can be so high. So that is the idea as a supercapacitor, electric double layer supercapacitor. Now, another thing that has been found in the past like 10 years or so is effects of confinement on the capacitor, right? And what they show in 2006 here is that if you use a porous material and you use ionic liquid, and it turned out that when you try to make a smaller pore, what is found is that at some point the ions start to be dissolved, right? And you start to lose all the solvents or counter ion around you, and become so close to the wall of the pore, and that suddenly increase the capacitance so much, right? So after that, I mean, it's a whole lot of ideas about, well, we need to understand how to further improve the performance of supercapacitor. Is really basically understand the effects of morphologies of the electrode, understand the effects of electronic properties of electrode, but also try to understand the pore size and what is the effects of electrolyte. If you change electrolyte, how does that influence my performance? So that is some of the work that we has been doing so far and try to help the experiments. So the first work that I want to show here is about the you know, graphene-based supercapacitor. So, you know, like this one, carbon-based chip, good conductivities, but the only problem is that, you know, it doesn't have a whole lot of, if it's not this type graphene-based material, it does not store a lot of electron, because, you know, there is not a whole lot of state around the family level that can store the electron. So the idea here is really incorporate something like C60 in the system, because you can really store a lot of electron in the C60, right? So what we show here is that, yes, I mean, when you include the C60 in the system, well, you actually increase a lot of state around the family level, and that certainly improve the performance of the device. That is also shown in the experiments. Now, but then another thing that we really find interesting, that is very hard to really understand from the experiments only, is that when you compare the performance of the system with a C60 and without C60, what we find is that it's not only changed the response of the electrode by itself, but also it's also changed the response of the electric double layer. And the reason it changed the electric double layer capacitance is that, you know, is because of the morphologies of the system. Because the C60 is on the surface here, when you charge it, it becomes so, the electrons are so localized around the C60, and then that totally changed the response of the electric double layer, and that even increased further the capacitance of the system. So this is one example where we show that, you know, you can really play with the morphologies of the electrode. You can also play with electronic properties in order to enhance the capacitance of the system. Another thing that we try to look at is that you understand the effects of electrolyte, right? Now, if I change electrolyte, how does that change my performance? And this is the experiment that they have. And so the collaborator found that, you know, basically, if you try lithium chloride, sodium chloride, potassium chloride, cesium chloride, so on and so forth, what we find is that the performance or the capacitance is actually increased if we go from lithium to cesium, right? So that is experiment measurements. And then how do we understand this from the simulations? So what we did is, you know, we create a pore like this, and then we try to compute two things. One is how much energy you need to bring the ion from the bulk solution into the pore. So what we find is that, you know, for the larger ion like cesium, the barrier for the ion transport into the pore is actually very low. And for the smaller ion like lithium, it actually have a whole lot of energies to go into the pore. Turn out that, you know, it is very easy to understand. It's because of dehydration penalty is so high for smaller ion or like lithium. So that using the pore is actually help, you know, enhance the selectivities. And that's the reason why cesium is easier to get into the pore. And that's the reason why it provide a better capacitance. That is one reason. But another reason is that one is getting to the pore is actually see that the decrease of the charge transfer between the larger ion like lithium or potassium is much larger, because these ion, it has the electron cloud around it is very flexible. It's really easy to go and, you know, transfer into the electrode, and that is another reason why, you know, you can even increase further the capacitance. So, you know, what we show here is that, you know, by using simulation and modeling, you can understand and even suggest like, what type of electrolyte should use, and also understand the underlying mechanisms of the, capacity performance. So the last thing I want to show, hopefully going really quick here, is about using simulations and modelings to understand separations and water treatment. And two systems we want to talk about today is one is so-called the capacity ionizations, and the way it works is pretty simple. So you have a two electrode here, and then you have a salty water coming in, and then you apply potential. And so cation go one side, anion the other side, and then you have a pure water as an outcome, right? As the output. Another platform that we has been working on in Livermore is about the carbon nanotube, and then here certainly you don't apply potential, mostly driven by pressure or gradient, concentration gradient. But then overall, what we really want to do in these two platforms for the simulations and modeling is to understand the mechanisms of ion selectivity. In particular, we want to understand like how ion selectivity depends on the size, the shape of the ion, also the valence of the ion, and also how does that depends on the pore size, the chemistry, and so on and so forth, right? So this is the first thing that we look is to understand the transport of water through the carbon nanotube, and then this simulation set up here. In this case, we use classical simulations. So what we show here is that the barrier for water transport in this system is really low, like 3 kcal per mole, which is consistent with a lot of previous study, and simply because the energy to break the hydrogen bond of water to get into the pore is quite low. Now we also look at the other ion like chloride, and we find that the barrier for chloride through this system is very high, much more like 4 or 5 times higher than water, and the same reason is the barrier actually determined by the dehydration process. You need to really break a number of water molecules in order to have the chloride get into the pore here. So in this case, you see like it needs to lose at least like 4 or 5 water, 4 maybe, to get into the pore here. So that the energy penalty is high. So this sort of tells us like the first mechanisms about the ion selectivity is dehydrations, which is well known. And the questions that we see here is, is a barrier of 3 kcal per mole for water. It makes sense, right? So if we look at the sort of the current understandings of what is the strength of the hydrogen bond, it about like 5 kcal per mole, right? So in this case, once you have the water entering the pore here, it loses about like 2 hydrogen bonds. So if you do a simple math, and then the observation energy is going to be like 10 k per mole, right? So it's much higher than what we see or calculations that we show before, like 3 kcal per mole. But turn out that this picture is obtained in the gas phase, and really when you put these 2 water molecules in the solutions, and then everything going to be screening, it's going to be screened by other water molecule, and then the hydrogen bond going to be much weaker. So that's the reason why the hydrogen's energies of water in the solutions is way smaller, about like 6 kcal per mole. So if you divide that by 2, it sort of give you the barrier for water as what we compute in these calculations. But overall, what we show here is that the transport of water through carbon nanotube is fast because the barrier is low, and then for the ion, it's not, because actually you have to remove a whole lot of water around that. So the dehydration of water of ion is one mechanism, but another thing that we really want to understand is there anything else, right? So that we turn into another platform. This one is slip pore instead of carbon nanotube, and we was looking into different ion. In this case, nitrate, because it's not spherical. It's a different. It has different shape, right? And then what we show here in experiment is that, well, here's a amount of ion that is absorbed by the system, and you see that nitrate absorbs so well. Chloride is not a whole lot. So now so what is the reason why nitrate absorbs so well, right? Why it's getting to the pore so easily? And then we compute the barrier for the ion to get into the pore, and what we find is that yes, the barrier for the nitrate is way lower than chloride for some reason, right? So that also consistent with the experiments. But we also want to understand a little bit better. So it turned out that there is a certain uniqueness about the shape of the ion, in this case nitrate, because the materials that we have is slit pore, right? And then for the nitrate, it can orient in a certain way. It can fit so well to the slit pore. So that's the reason why, the barrier for the ion transport is so low. And also that's the reason why the nitrate can absorb so well in this system. So this is another sort of example of how we use simulations and modeling to understand materials for, like separation, selectivity, and so on. The last slide that I want to show is about, again, what else, right? Is there anything else? So it turned out that, it can be even more complicated if we look into the ion with different valency. So in this case, we have a calcium and sodium. And what we found here is that, when we looking at the larger pore size here. So what we found is that if we have the pore that is large enough, turn out that calcium actually absorbs better, even though it has a higher penalty for the dehydration, right? But then when you start to turn on the higher potential, and then the degrees of absorption between calcium and sodium becomes so similar. So the behavior becomes very complicated. So that's where the simulations can be useful. So what we found is that if you have the pore that is large enough, it turned out that the whole ion of calcium in this way, with the whole solvation shell that it carries with it, can get in the pore at a very low barrier. It doesn't need to actually break any, break the first solvation shell, so that the barrier is low. And that's why it absorbs so well. But then when you start to apply a high potential, and then you start to have like sodium, in this case, the yellow one here, because it has a weaker solvation shell, the potential start to actually try to break the solvation shell sodium first. And then at that point, you actually start to have a similar absorption degrees absorptions between sodium and calcium. Yeah, so the story is complicated, but all I want to show in this slide is that, beyond the dehydration, ion selectivity is governed by a whole other thing: the pore size, valency, dehydrations, and applied potential. And all of these effects can only be understood if we have the simulations and modelings to really look at that different effect. So that comes to the final slide here. Hopefully I try to convince everybody that understanding material is the interface is a key element for the advancements in materials and material performance. And also simulations and modeling, I truly believe that is a powerful method for understanding and predicting material properties. And it's going to be even more exciting in the near future about using simulations, data science, and AL to understand, to accelerate material developments. So with that, thanks everybody for chiming, for hopping in, and a lot of thanks to wonderful people that I have been working with, and open for any questions. Thanks.
Thanks a lot, and Tuan Anh, I think I speak for everyone here that we all really appreciate your talk and the knowledge that you provide us with. So now moving on to the Q&A session. If anyone here has a question for Dr. Pham, please raise your hand or you know, unmute yourself and ask question directly to Dr. Pham. I think I see one hand here from Việt Anh. Can you please unmute yourself and turn on your videos and whatnot and ask a question? Thank you.
Yeah, thank you. Hello, anh Tuan Anh. Thank you for your very nice talk and a lot of amazing results. I have a question about the methodology. So all the system should be simulated at the very large scale. So I wonder, like, you're using the localized orbital basis sets in the simulation?
Good to see you, Việt Anh. I know that you in Texas now.
Okay, you still remember me. Okay.
Yeah, I know. With Feliciano, I'm gonna see him in the fall. Yeah, love the guy. Well, it's a good group. Good. Yeah. Yeah. For the questions, it's really about the system that that we are doing, right? So, one thing for the tire simulations, for example, so for the separations here, everything was done by classical simulation. So we don't do any quantum simulations. Actually, yes. For this separation, we actually try to compute the barrier for water and ion transport by using hybrid approach. And the model is quite small. So we build a sort of maybe like 100 to 150 atoms. And then the solution is a classical, right? It's a implicit solution solvation. So it's cheap. But then for all the FD calculations here, the system is about, let's say, 300 atoms or so. So it's still doable with the plane wave basic test. So everything was done with the plane wave. Yeah.
Oh, never. I mean, 300 atom with plane wave. I mean, it's still doable with plane wave. So.
Yeah. I still like for water, like this system. I believe we have.
Okay, but so sorry for interrupting, but you're doing that with DFT level or GW or hybrid?
Yeah, so both, right? So this one we really burn a lot of simulation time to do the GW, and for this paper is we actually use DFT for the MD, and then we take the snapshot, like 20, 30 snapshot, and then we use that snapshot for the GW calculation. So it's a lot of simulation time. We burn a lot of high performance computing.
Okay, I see.
Yeah, this one we use a hybrid, and again it's cheaper than GW, but then it still is a lot of simulation time, a lot of calculations for the electronic structure calculation for this one. Not a whole lot for the MD. The MD is fine, especially these days. You can do the system of 200 atoms pretty easily. Well, just take some time, but the help
it's doable.
Really well.
Okay, yeah, I think. And yeah, one more question. Like the GW you mentioned in I guess it's this the GW method developed by Julia Galli group that don't need many empty state get involved, right?
Yeah. So that dates back to the time that I was in the grad school, and yes, so the very first thing that we try is after testing the sort of silicon and those things, is really try to look at the liquid, and then it sort of get better and better, and the performance is better. So so that we use that approach to look at the liquid and the salty solution. Yes, exactly.
Okay. Yeah, thank you so much.
Yeah, well, good to see you.
Yeah.
Thank you, Tuan Anh, for the very detailed answer. We have a question from Facebook from, I think his name is Dai. How big is the supercell for your water system with surface? And do you consider it at GW as well?
Oh, that's a very good point. So for the supercell, actually, I don't remember. I remember that the system is about 128 atoms. So yeah, it's like 400 atoms. Oh, I'm sorry, 128 water molecule. So you times 3 of that, you have the number of atoms. Now, it's a good question though, like how we compute the energy level of that surface. We didn't really directly apply the GW approach for that. I think we had a bunch of correction in there. So we come up with a scheme to sort of compute the change in the electronic structure of the surface, but directly apply the many-body perturbation theory for that surface is still too expensive. I would say that is a sort of maybe like similar to that is about these calculations about the interface between a solid and a liquid. And in this case, we actually also, we didn't really apply the GW calculation for this system, for this directly to the interface, but then we sort of apply the corrections to the liquid and then the corrections to the solid, and then we align everything together. For the calculations for the whole interface is still like very challenging at this point.
Thank you, Tuan Anh. Is there any other question for Dr. Pham?
Oh, go ahead.
Oops. Anton, can you please go ahead first? Then probably Ji-Hương here.
Chào anh Tuan Anh, mình là anh Tuấn. Mình có một câu hỏi ở slide number 23 about supercapacitor. Yeah. So previously you mentioned that when the pore size is small, we can obtain a higher supercapacitor. But in this slide you have a C60 in between the graphene layer, right?
Yeah, it's actually I should say that it's not a porous material. So it's actually a flat. It's actually two different systems. I think I didn't make it very clear. So this one is sort of more like graphene sheet, right? So and then you put a C60 on top of it, right? And the idea is now this system is not a porous system. It's just graphene only, and then you put a C60 and see how the performance is changed. And then this one is a porous material. It's sort of different system. Yeah, I didn't explain it very well.
Okay, thanks. Yeah.
By the way, it's interesting. I should say we had a discussion with your advisor, and then in another meeting, and then he said, "Oh, there are so many people with a similar name like Anh Tuấn and Pham, sort of okay. It's sort of interesting. So
yeah,
we should catch up at some point."
Yeah, thanks. Yeah.
Okay.
There's another question from Công Vũ from Facebook, and I guess this is one of those questions that theoretical physicists and simulators always got asked. Ankong asked, thank you very much for your great talk. I am concerned about the reliability of the simulation, especially for complex systems. Whatever you input in the simulation system, it will probably give out outputs. You might have to compare them with the reported experiment results, assuming that there are so many results that might report different or even opposite results, especially for the topics that have been controversial. How would you deal with that?
Yeah, it's a wonderful point. I mean, it's a excellent point, and I think we have to be very careful about that, and that's the reason why in almost all the activities that we have been doing is we work very closely with experiments partner. So in our team, we have the simulations, like us, and then at the same time, there is a people doing characterization, synthesis by measurements. And usually it's not like, well, let's go and do these simulations and then report it. It's always there is a lot of back and forth, discussion between the experiments and theory. So usually the way it works is they're gonna start and tell us like, hey, this is how the material look like, and then we start to use that input to look into the model, and then we compute, we predict something, and then we go back and talk to them that, hey, this is what I'm finding. And they say, no, maybe it doesn't make sense. It's totally different from what we find. And then at that point, we start to include, or, we try to improve the complexities in the system, or you change the model, or you improve the method. We try to become more accurate. So I totally agree with that. And the only solutions that really we see as, and sort of go back to this slide, is the paradigm is really by integrations between simulation, experiments, and data science. You cannot rely on simulation only, and also, for the experiments only, it's going to be really hard to understand different effects. So I would say that, it's really about, you think things about simulation as a one special type experiment, right? Hope that I understand, sort of answer that question. So
thank you, Tuan Anh. Our VCA team from Ji Hương also has another question for you as well. Ji Hương, can you unmute?
Yep. Hi, Tuan Anh. Thanks for a great talk. I just have a question. Could you comment on, especially when you mentioned earlier when the use of machine learning is on the rise on computational chemistry, could you comment on possibility of using machine learning on complex system like the ones that you presented here in this talk? Like, what are the challenges? Is it possible yet to use machine learning on this type of research? Or
well,
is it quite futuristic?
Yeah. Well, I really believe that, right? So I think it's still a lot of work need to be done, and we really, I'm not present anything today because I think that we're still a little bit, especially for me, I haven't really have a full understanding of that. But then we already start to have that activities in a lot in Livermore, but especially in the material science. Like what we are trying to do right now in our group is to really going beyond simulations and experiments only, but try to incorporate data science and machine learning. So there are many ways, really many ways we can use simulations and modeling to understand material science. So one thing is about reaching the scale. So what it means is, well, I know how to do these simulations for nanoscale. It is expensive, right? It's very expensive, but it's accurate, let's say. And then if I move on, maybe this one is better. So I know this calculation, I know how to compute it. It's accurate, but it's slow. This one, I know that is fast, it's a little bit less accurate, right? So how do we bridge the gap between these two type simulation? Can we do something like fast and at the same time accurate, right? So that is the role of machine learning. It's a whole lot of work it's doing right now. Is like try to use information from the high fidelity simulations and use that information to train a model that now it can do it faster. So that's one thing. Now, another thing that is really interesting to look at right now is the machine learning and data science, the role of how to really accelerate the integrations between the experiments and simulation, right? So now I have information from experiments. Can I interpret that faster? And that is a role of machine learning and data science. So it's another way of doing that, and it's really blooming right now. It's a lot of things has been doing in that direction. So it's going to be really exciting. Yeah. So just a few examples that that is thinking about. One is to accelerate the simulation by itself. Second is to really accelerate the feedback loop between simulation and experiment, and eventually sort of going toward the ultimate graphization synthesis as well, right? So I really think that data science and machine learning have a big role in the coming years. And right now, it's very clear from the departments of energy that everything that they really have a lot of investments on that directions. And it's not only like you see that in US, but also in Europe. There are a lot of activities right now in Europe, and then also even we see that in Vietnam as well, right? The role of try to use data science for a certain, maybe not for material science study at this basic science level, but it become more and more opportunities in that directions, I would say, and it's moving very fast, right?
Thank you. And just a follow up with that, because you mentioned that we need to accelerate the feedback loop between machine learning experiments as well, right? So my understanding is that we need quite a large amount of experimental data to feed into the model to train the learning model. Is there a specific field in material science that you think that may provide more abundancy of data for machine learning than others, and where we can see more opportunities for machine learning because the availability of experimental data?
Yeah, it's a very good point. Actually, it's wonderful questions, and this actually the problem that we has been hitting very recently. So everybody excited about machine learning, data science, right? So now we had the experts on machine learning working with us, and then they ask, okay, where's the data? I don't have the data. So the data from experiments going to be sometimes is challenging, especially that you relies on the certain facility you have to wait for a long time. So certainly is a challenge, but what we can do to sort of help that is go back and use this, right? Now, instead of creating the real experimental data, you sort of create a sort of synthetic data using simulation and modeling, right? So let's say I want to look at the X-ray spectrums of material, and I need to do a lot of experiments. Yes, that is one way to build the data, but another way to do that is, well, let's say I create a structure using simulation and modeling, and then I use those structure, I compute the X-ray spectrums. So I have a database of X-ray from simulations and modeling. So I have one database from simulation. I have another real database from experiments, and then you can combine them together. You can also complement. You can also sort of go back, use experiments, database, sort of try to benchmark the simulation database. So that's the reason. That's one way to sort of collect more data, because now the simulation is really we have a big machine, and we can really create a lot of data. So I think for that a lot a lot of work. I think that recently quite a bit of work has been put in that direction, like using simulation and modeling to create a data that can complement the experiment data.
That's a very interesting approach. So basically using well-established model based on first principles to create data to come for experimental data. Okay.
And it has to, it's come to the point, the reason why we can do that, right, is again, it's because creating two things here. One is that, well, the modeling at this point is not perfect, but it's sort of reliable in a way enough that you can sort of use that, right? And to complement the experiments. Another thing that is very interesting is, which is really important, is if you create the model by simulations, you know what it is, and then you can really create, like, you have a model, you have a structure, you know exactly what it is, and then you compute something. Now you have the one-to-one corresponding between the structure and the property. That's something you can control, but for the experiment you cannot do that, right?
Yeah, thank you so much. And
yeah, excellent question. That's exactly what we just discussed this afternoon. So
thanks a lot. And so if no one else has any other question,
can I have another one?
Oh, I don't. Yes, of course.
I think so most of the property you calculate kind of thermodynamics property. Have you tried to calculate the transport property, for example, the water transport through the carbon nanotube or graphene?
You mean like using MD?
Both.
Yeah, we are. Well, yeah. So for these things, we actually very recently published a paper on JCTC or something. Try to look at the ion diffusions of ion in the CNT, and the idea of that is, like we sort of see what is the effects of difference approximation that you use for the ion water, ion pore transport, like polarizability, cation pi interactions, and those things. So yes, we has been using classical simulations to look at the diffusion of ion in the carbon nanotubes. So certainly it can be done with classical simulations. We has also been using first principle to look at the ion and water transport in this porous material. But the thing that is really concerning is a limitation, is a time scale, right? And we don't have enough statistics. Well, let's say we do. Let's say you want to look at the MOS tube, right? You put an ion in the pore, and then you run the MD with the first principle. At most, you can deal with like 400 atoms. So basically, that's one ion in the solution. So the statistic is so poor, and we don't have enough statistic to understand the transport. So that is one limitation. Now, there is one proposed sort of one idea that we have been picking around, and I think it's going to be really interesting to try, is going back to the ideas of machine learning and data science, is that well, let's do this atomistic simulation, right? And using that as a training set to build a new type of force field, right? And then use that to really run a longer time, so you can look at the dynamics. So some of that has been some of the work has been done by people in Princeton, for example, like they try to use first principle calculations to create the data sets to train the new force field and model to look at the transport. Yeah. But the transport here, I really think that transport for the complex system is really interesting. It's just so much challenge to do that.
Thank you, Antonin. I think we have another question from Phùng Việt Bắc from Vietnam Japan University. Thank you for your great talk. I am aware of the problems of charge assignment based on plane wave calculations. Should affect the absolute charge quantity. The loss or gain of electrons should not be influenced. Is it a correct interpretation? If so, how can I judge the direction of electron flow?
See, let me read that. So the directions of electron flow. Well, yeah, I think it's totally, again, it's a great question. I think like charge localizations is a big problem for first principle calculations, especially like, you know, all the calculations that I showed today. Other than this, I guess like about the supercapacitor here. I mean, this calculation was done with a DFT, right? So we know that with DFTs there is a problem with the localizations, charge localization, electron delocalization. That is a problem. So I think the absolute value that we report here may depend on the levels theory, but the trend between the ion, like between like lithium, sodium, potassium, cesium, the trend gonna be consistent, and that is the story that we want to tell, right? The absolute value, yes, gonna be had concern, but then the story, like the trend between the ion, gonna be consistent. I expect that, you know, you do a higher levels theory calculation, they're gonna see the same thing. So hopefully that is a answer the question. So.
Thank you, Antonin. If there is no question, I guess.
One
Okay.
please.
Sorry. Yeah.
Do you think the van der Waals direction is important in the field of your system? And did you do that?
Yeah, actually, it's a very good point. Yeah, it's actually very important. So so van der Waals interaction, we include that in these calculations. Again, I think we test the trend. If we just do DFT and then we do DFT with van der Waals corrections, the charge transfer sort of, well, the trend is similar. So it's not really important in this context. But then another thing that we try is we look at well, let's say we do the rear MD simulation when you put the water in the MOS2, right? And then we test two things. One, without the van der Waals correction, another one is with the van der Waals corrections, and then we see that you know, the behavior of the layer is actually different with the van der Waals corrections. Yes. So long story short, I think for the layer system, van der Waals correction is very important. That is well known in the literature.
Yeah. Okay. Yeah.
Is there any other question? So with that, I'll end the screen sharing from Antonin and pass the mic to Chị Nhân for the ending.
Dạ. Em xin cảm ơn anh Tuấn Anh rất là nhiều với phần trình bày rất là thú vị, ấn tượng về kỹ thuật mô phỏng trong dự đoán và hiểu tính chất vật liệu. Em cũng xin cảm ơn mọi người đã tham gia chương trình, đặc biệt là anh Tuấn Anh. Thì anh, trước khi mà kết thúc chương trình thì em muốn hỏi anh là anh có lời nhắn nhủ gì với mọi người đang theo dõi chương trình ngày hôm nay không ạ?
Thực sự mình nghĩ là cái really happy about this, tức là cái activity mà các bạn đang làm nó rất là ý nghĩa. Thực sự là ấn tượng, bởi vì là những cái thứ đấy thì những cái thứ này thì có thể là cái generation của bọn mình thì đã rất muốn làm rồi, nhưng mà nó chưa có cơ hội, hoặc là nó chưa biết cách làm. Thì bây giờ là với cái hoạt động bây giờ mình thấy là nó rất là hữu ích, là mình build một cái community, Vietnamese community for scientific community is so important. Mình nghĩ rằng là we have good people, but one thing that we don't have is really we don't have a community, right? And now if we are able to build that, then it's not only like to help the people anywhere, but also it sort of open a lot of opportunities for young people, like the student. We can help them. We can help them to learn a way how to send applications, how to look for a job, and build your career either here or go back home. And also another thing is to have the connections between the people from starting approach, or people like working anywhere like UK, US, whatever, and the people like working in Vietnam, right? And then we can build a connection there and make everything better. I think there is a few opportunities to improve the science that we want to do. So it's great. So thực sự là mình muốn cảm ơn các bạn về làm chuyện đấy. Nếu mà có một cái mình muốn nhắn nhủ cho những các bạn trẻ hơn mình chẳng hạn, là thì thực sự là cái có lẽ quan trọng nhất là cái dream, đúng không? Mình có một cái hoài bão, một cái giấc mơ, mình có một ước mơ, mình muốn một cái gì đấy, something meaningful. That's what you want to do in your life. Go for it. Don't afraid, and put your time on it. Thì cái đấy là cái quan trọng. Một cái nữa là dream big. You never know, right? Yeah, try the best and dream big. And that's very important. Another thing is that another thing that is very important is to care about the communities and try to build the connections. It's extremely important. It's extremely important. It's not only about the good work, but also the person that you know, right? And so you need to. It's like doing business. It's the same thing. So you need to sell the product to the right people, and it requires some understanding, some work. So don't stay in the office. Don't stay in the lab all the time. Go out. Go for lunch. Talk to some people, and that's how you know people. It's very important. Thì đấy là những cái mình nghĩ là nó quan trọng. Còn một cái điều cuối cùng là really rất là happy với cái opportunities này, that is really open to any suggestions, and also if there is anything I can help, I promise I'm going to do the best from my end to help like the community. So just let me know, shoot me an email, happy to do that.
Dạ, em cảm ơn những cái chia sẻ rất là tuyệt vời của anh. Thì ở đây em thấy ở trên Zoom á, có anh Việt Bắc Phùng á, anh hỏi là can you share your presentation prior? Thì có lẽ là là em cũng hỏi anh luôn. Dạ.
Cái này thì những cái material này thì nó hơi sensitive một chút, tức là đấy là của mình làm, nhưng mà ở chỗ mình thì nó là national lab, cho nên đôi khi nó hơi tricky một chút, nhưng mà again we can talk, right? All the paper is published, so I can send it to you. Nếu mà bạn muốn thì mình có thể send cái list of papers. It's nothing secret. It's all over the place, and shoot me an email. Certainly. Mình có thể làm chuyện này.
Dạ vâng. Vậy một lần nữa là em xin được cảm ơn anh Tuấn Anh rất là nhiều, và mọi người đã ủng hộ đóng góp cho nhóm ngày càng vững mạnh hơn. Thì nhóm sẽ sau cái buổi webinar hôm nay thì nhóm sẽ gửi một cái feedback form để cùng với lại video được post lên YouTube để mọi người có thể xem lại và có thể feedback lại để cho những cái buổi webinar tiếp theo là tụi em có thể làm tốt hơn. Dạ, và chúc mọi người cuối tuần vui vẻ. Enjoy your weekend.
Thank you. Thank you
Dạ,
everybody.
cảm ơn mọi người rất nhiều. Cảm ơn anh rất nhiều. Dạ,
Thank
bye
you.
anh.
Bye guys.
Bye. Bye guys.